today's lecture, we are going to discuss about a different kind of image segmentation technique that is based on similarity, that is known as Hough Transform. So Hough Transform is a global processing technique in a situation where only an edge image is available and no knowledge about the pixels belonging to the object is available. Edge linking can be performed based on global properties. So Hough transform can be used to detect lines, circles and other parametric curves. Edge detection can be used as a pre-processing to detect the image pixels on the desired curve. Due to imperfection in either the image data or the edge detector, there may be missing points or error in the edge detection. So Hough transform is used to group edge points into object candidates by performing a voting procedure. So Hough transform is a technique which can be used to isolate features of a particular shape within an image. So this transform is a mapping from a spatial domain or image space to a parameter space. So what is parameter space? As you know that in the case of image space or spatial domain, y is equal to mx plus b represents a straight line. Now, if we are going to convert into a parameter space, that is b and m, so then the equation can be expressed as b is equal to minus times of mx plus y. So here, if we have a straight line in a spatial domain, so they have the fixed slope as well as intercept on the y-axis. So slope is representing by m and b represent the intercept on the y-axis. So they have a fixed value. So in the parameter domain in which is plot between the m and b, so that can be represented by a single point. Now, when there is a point in the image plane or spatial domain, then how it would be represented in a parameter space. So as you know, in the parameter space, b is equal to minus mx plus y. Since we have a point in the spatial domain, for example 1 comma 1, so now b will become minus times m plus 1, which is an equation of a straight line. So a point in the spatial domain can be represented as a straight line in the parameter space. So we have been seeing two cases, that is, first one is a straight line in a xy plane or spatial domain is mapped to a point in the MB plane, and in the other case a point in the xy plane that is mapped to a straight line in the MB plane, and this is the basis of Hough transformation. So by using which we can link the different edge points which are present in the image domain or spatial domain. So for example, if we have more than one points in our image space or spatial domain, for example x of I and y of I, x of j and y of j. So now these 2 points are represented by two straight lines in a parameter space. So as you can see, corresponding to red, this one is a straight line, and corresponding to this blue, this one is a straight line. These straight lines intersect each other at a particular point. So now if there is a more than 2 points, for example if there is 3 points, so these are going to be represented by 3 straight lines in a parameter space. So they are intersect at a particular point. So as you can see that two straight lines, this one and this one, or 3 straight lines meets at this particular point. This is the one which gives me the value of m and b. So this will give the value of m and b, which is nothing but the parameters of the straight line in the xy plane. this M and B, if we are going to join these 3 points, so we will get a straight line in the xy plane, and that have a particular value of slope as well as intersect value on the y-axis. So this M and B are nothing but those M and B value which are in the image space. So all these straight lines are corresponding to the point which are collinear in the xy plane and pass through the intersect at a single point, and this point in this case is M comma B, the values which represent the straight line in the xy plane. Now, for example, if that point is not a collinear to these 3 points, so this will be represented by a different straight line. So that will not intersect at this point. Now, how to compute this Hough transform? As you know that in the digital cases, since images are digital, we cannot have a continuous values of B and M. So now M and B plane is divided into number of small accumulator. Here we assume that there are n number of points in the xy plane which are collinears. So now we have divided M and B plane into number of sub images whose values will ranges from B minimum to B max and M minimum to M max. Now initialize the accumulator value equal to 0. So for example, this accumulator value is represented by A of I comma j. So first we have to initialize this one, A I comma j is equal to 0 for every element of M comma B or I comma j. Now for each image edge x of I and y of I, for each element of A M comma B, if M comma B lies on the line y minus mx is equal to b, means they are collinear, then increment A M comma B is by 1. And after that, once you scan the whole image, then find the local minima in this accumulator. Now, for example, you can see that here number of points which are collinears. For example, this one, these are the collinear, 6 collinear points. These are the 5 collinear points. These are again 6 collinear points. These are 3 collinear points, and these are 5 collinear points. So now these collinear points are going to be accumulate on accumulator. So this 6, for example, here, then this 6 representing by accumulate in this accumulator, and similarly we have allotted 3, 5 and 5. Now we have to take a threshold value. So for example, if I am taking a threshold value of 3, then all these 3 points are going, then all these points are going to be connected. If I am taking a threshold of 3. But what if I am going to take the threshold of value greater than or equal to 4? So now there will be a no line here. So now it will be connected in this manner. So its accuracy depends upon how many number of accumulator cell I will have in the accumulator array. If I have a very large number of accumulator cells in the accumulator array, then the accuracy of the computed M and B will be quite high. Whereas if I have a small number of accumulator cells in our accumulator array, then the accuracy of this computed value will be quite less. As you know that that slope can vary from minus infinite to plus infinite. For example, when theta is equal to 90 degree, in that case m is equal to tan of theta becomes plus infinite. Similarly, c can vary from minus infinite to plus infinite. It means we need a huge memory. So in this method we do not take when m becomes very large or infinite. So instead of considering the slope intercept, from what we can do is that we can use a normal representation of the straight line, that is represented by x cos theta plus y sin theta is equal to rho, where rho is a length of perpendicular drop on the line, drop from the line to the origin in the xy plane, and theta is the angle made by the perpendicular with the x-axis, and theta can vary from 0 to 2 pi or from minus 90 to plus 90, and rho can vary from 0 to rho max, and this will make a finite accumulator array size. So now this represent a image space. So now we have to find out how we are going to represent from image space to Hough space, that is rho versus theta space. So similarly, you know that if a point in xy plane is 1 comma 1, then if we are going to represent it in a parameter space or Hough space, for example here xi is equal to 1 and y of I is equal to 1. So now if we are going to represent it with the help of normal representation, then rho is equal to x cos theta, x is 1, so 1 cos theta plus 1 sin theta. So rho is equal to cos theta plus sin theta. So this point is going to be represented by a sinusoidal waveform. So a point becomes a wave in a Hough space if we are going to represent it by a normal representation of the straight line. Similarly, if we are going to take a straight line, then it has a particular slope and intercept values. So now it is going to be represented by a single point. Now if we are going to change the slope, then this point, location of this point will be changed. Similarly, if you are going to move on the change the slope, then the location of the point in the parameter space will be changing. So now, for example, if we have 3 points which are collinear to each other and there is another point which is non-collinear. So corresponding to each point there is a one sinusoidal waveform. So as you know that these 3 points are collinear, so they are going to intersect at a particular point. And this point is not collinear to these 3 points, so this will not cut at this position. But of course these 2 points are collinear, so they are going to, or these 2 points are collinear, or these 2 points are collinear, so they are going to cut this graph. Now, so to represent it in a Hough space, so we have to initialize the accumulator S to all zeros for each h point x comma y in the image, and for theta will vary from 0 to 180 degree, or you can also vary from minus 90 to plus 90. For example, for each point rho is equal to x cos theta plus y sin theta. We have an h point x and y that has already been given. So now we are going to change the value of theta from 0 to 180 degree, and corresponding h rho we are going to calculate, and for that h theta comma p, for every h point it is going to be incremented by 1. Now the find the values of theta and rho, where h of theta comma rho is a local maxima. The detected lines in the image is given by rho is equal to x cos theta plus y sin theta. So I am going to explain it with the help of this example. For example, there is a 1 point, this one. So it will be represented by a sinusoidal waveform. Then there is another point which is again going to be represented by another waveform, sinusoidal waveform. As you know, these 2 points are collinear to each other, so they are going to intersect at a particular point. Similarly, all these 3 points are collinear, so they are going to be represented by a sinusoidal waveform, and finally they are going to cut at a particular point. So how we are going to use this Hough transformation to find out the edges? So this is a basic illustration of Hough transform. Here there are 5 points, 1, 2, 3, 4 and 5. So now 1 point which is on the origin. So x is equal to 0 and y is equal to 0. So rho will become 0. So that is going to be represented by this straight line. Now this 2, which is a collinear to 1, so this is going to be represented by a sinusoidal waveform, which is this one. And since 1 and 2 are collinear, so they are going to be intersect at particular point. Now 2 and 5 are collinear, so again 5 is going to cut 2 at a particular point. So this waveform represents a 5 which is intersect it at Q. Similarly 5 and 4 are collinear, so 4 is going to be represented by this waveform and it is going to cut 5 at this position. Now 4 and 1 are also collinear, so they are going to be cut at this position at S. Now you can find that there are two intersect points that are going to be represented by A and B. So at B, 3, 2 and 4 are intersect. 3, 2 and 4. These 3 points are collinear to each other. So they are going to intersect at a particular point which is represented by B. Now 1, 3, 5 are also a collinear. So they are going to cut at particular point which is represented by A. Now this is a basic example of Hough transform. You can see this one is an aerial image and we have to detect this runway. If we are going to use a canny edge detection, then we will get this image. For using, if you are going to use a Hough transform, so as you know that this line is oriented in the north direction, so theta is equal to 90 degree and all these points are collinear, so they are going to intersect at particular point. So since all these points are collinear, so there for every point there will be an increment of accumulator. So a of j comma I comma j is going to be increment for each point that is present on this runway. And after selecting the local minima, we are going to get a edge detected output. This is another example of Hough transform. In here we are going to get a edges information. So these are the 20 most prominent lines that are we are going to get with the help of Hough transform. And this is corresponding a Hough parameter space in which where every point is going to be represented by a waveform. And if these points are collinear, then they are going to cut at particular point. So advantages: simple and easy to implement, handles missing and occult data gracefully, can be adapted to many types of forms other than lines. Disadvantages: high complexity for objects with many parameters, look for only one type of object. The length and position of the line cannot be determined. Collinear segments cannot be separated. Thank you.